So you know Darcy's law. We've written it a variety of different ways. So volumetric flow rate, Darcy velocity times area. Certainly the assignments that you've done, you've been able to do them by writing it in this way, where you can define permeability as some kind of hydraulic conductivity as some kind of equivalent hydraulic conductivity. If you're given a permeability, you can always convert between one and the other by knowing that this is hydraulic conductivity, right? And this is perm. And you should know all of these properties. We've been very consistent about them. This is viscosity of the liquid, dynamic viscosity, and this is density and gravity. So we've used those throughout. So you know that you can use that to get a Darcy velocity, just from what we've done today, right? We said Darcy velocity is equal to minus k dH dx. If you know Darcy velocity, you can always convert it to the advector velocity, which is the one we've used for transport just by dividing by porosity. And you've certainly done that a number of times, and so you know that. We've certainly talked about the permeability of fractured systems, fractured rocks, and you've kind of used that to back calculate entry pressures, where the spacing between fractures is some amount, and the apertures of individual fractures are some amount here. So you've certainly seen that, and you've certainly used that in your assignments. So those are some kind of background expressions that you've used. We talked about immiscible flow. So the behavior when a free product takes days to weeks to months to get to some initial location. We know that this capillary pressure versus saturation diagram is kind of important. It defines a bubbling pressure, and I guess this is recorded so you can actually go back to this. A bubbling pressure which allows you to push a bubble of this non-wetting phase into the system. We define it as the difference in pressure between the pressure in the non-wetting phase and the pressure in the wetting phase. And so it's just some kind of overpressure that we have to apply to be able to force this little bubble in. We can define it either as a pressure or as a product of a height of fluid and a unit weight. You've done that. We know that you can, bless you, define a drainage curve, called a drainage curve because you're draining water out as you go to the left, and an imbibition curve, whoops, as you're spontaneously imbibing water as you go to the right. And the other important coordinates on this are irreducible saturations, which are kind of blocked off by these portions. This is what, in a physical sense, this is the amount of water that's left in the system. This is the amount of NAPL that's left in the system that you can't get out. And so you know these kinds of no-go, no-go regions. I suppose not drawn here, but you certainly know in terms of flow behavior that these regions also carry through into looking at relative permeabilities. These kind of X plots that we have. This is also saturation of water. This is between 1 and 0, relative permeabilities. And this would be the relative permeability, I guess, for the wetting. 100% water, right, would be here. So this would be the wetting phase. And this one would be the non-wetting. And we talked about how those change. And so these are key diagrams to understand what's going on. We know that we can look at this entry pressure here in terms, I guess this should be really HC0, right, the entry pressure. And these entry pressures here should also be entry pressures given by the diameter of the pores or the aperture of the fractures allow us to calculate what that is. This value here is also, you'll remember, you've used this in a Leverett formulation. This is a J value is equal to about 0.3, I think we've used. And so there's a whole bunch of correlations you can use to you should know your way around these diagrams, I think, because that's quite important. So that's a basic behavior. Almost all the problems we've talked about, water is a wetting fluid, and either air or an apple is a non-wetting fluid. That's important because that allows you to really consider this really always, it's the wetting saturation. And so this is also water saturation, I guess is what I'm saying on the base here. Not just the wetting saturation, but it's typically the water saturation. And we talked about some expressions to be able to calculate, the height of this stuff that you'd have to get if you are sitting on top of the surface, which would be this one, right? And once you get this little ganglion present within the subsurface, then the height that you have to have for this, for it to keep going and to never stop, is given by this. This is HC0, I guess. And these are just the unit weights of the two different materials. So if you know what the bubbling entry pressure is, then you'd know what this is by just this relationship here. And if you know what this is as a material property, and if you know what the densities of the two fluids are, you could calculate this, and that would give you a length. And if you knew that your ganglion was longer than that length, then you'd surmise that it would just keep on going, never stop, was the basic idea. So that was another important concept that we talked about. We talked about Brooks-Corey plots, just as convenient ways to represent saturation versus bubbling pressures, typically divided by unit weights. These were log values, and they were just linear terms, which were basically this expression here, just stated in a different way. And so we went through those. We've used this in the past to describe behaviors. I've never used this. This has never appeared, I don't think, in an exam question, Van Genuften. But certainly Brooks-Corey has. And so that's just a different way of being able to draw these capillary pressure versus saturation curves. We talked about ways of being able to define relative permeabilities. And if we knew what relative permeabilities, we tried to make it relatively simple and basically say that you could calculate the flow velocities, the volume flow rates as equal to, you've done this calculation, I know, total area of the core times hydraulic conductivity times relative permeability, whatever the saturation is, times head gradient, right? dH/dx. And so this is the cross-sectional area of the core. This is the hydraulic conductivity. This is head and length. And this is just a value between 0 and 1, which represents what particular saturation you find yourself at. And so it's typically, I think it's easier conceptually to be able to calculate what the flow rate of the napple would be if you, or this would actually be the flow rate of the water in this particular case. If you know the hydraulic conductivity of the system when it's, so this is 100% saturated with something, with water, say. And if you know the cross-sectional area of your core, if you know what the relative permeability is, just going to be a number between 0 and 1. And if you know what the hydraulic gradient is, and it allows you to calculate the volumetric flow that will occur through your system. And so we certainly just defined it in these ways as well, but I think this is perhaps an easier way to get your head around. So I guess we're kind of running a bit low on time. So that's kind of the flow of multiphase fluids. We also talked about transport. We talked about advection dispersion equations. We talked about them again today. We basically made the case that if you look at behavior in terms of an equivalent dispersion and an equivalent advective velocity, where you divide just by the retardation coefficient, If you use those equivalent parameters, you can use any of the graphs or concepts that we looked at from Fetter. And those would correspond to, we always define them in terms of an upstream kind of input function, what it would look like in the core, and what it would look like at the downstream reservoir in terms of arrival times. And we defined them in terms of a couple of different parameters, I think. One was residence time, or non-dimensional residence time. One was a relative concentration, and one was a Peclet number, which, if it's not given here, Peclet number was what? A velocity times a length divided by dispersion. And this relative time, which I don't see on here, was equal to time. Can you remember? I'm looking for it to see if it exists. It has to be, it's non-dimensionalist, so it has to be, a velocity must be on the top and a length on the bottom, I think. So this is length over time. This is length. Yeah, so that's non-dimensional. So that's what that was. So this is advective velocity. And so we defined all these expressions in terms of those two parameters. So this certainly turned up in one exam question. And so the effective properties are divided through by retardation, if retardation exists. Retardation is 1 if it's not retarded. It's less than 1 if there's some effect. Dispersion we get from molecular diffusion behavior plus mechanical mixing. Mechanical mixing is defined in terms of this term, which is not a function of material properties so much as a function of the length of the plume, which is a curious outcome. And we can always get advective velocities from the stuff we had at the top of this page. Not sure we talked about that in much detail. We talked about using how to get distribution coefficients. I realize we're up against it, which we need here from data, from back analysis from natural gradient plumes, or from cases where we had a significant amount of organic carbon in the system. When we had multiple solutes, we had to use Raoult's law to look at the relative affinity of these multiple solutes to get the effective solubility of those. And we could also calculate the mass of contaminant that was present in an aquifer as a function of the concentration in the plume, the volume of the plume, the porosity of the aquifer, and also the retardation coefficient. We did a quick example. We also, ignore me. So we also did it for the Vadose zone. We looked at transport in the gas phase. We also defined the relative concentrations in terms of Raoult's law in function of the individual solubilities and the mole fractions. We defined the gas concentration as a function of the aqueous concentration through this non-dimensionalized Henry's law. In fact, the definition of Henry's law coefficient is just the ratio of the gaseous and the aqueous concentrations. And we defined the solid concentration as the equilibrium concentrations with the aqueous concentrations just through the distribution coefficient. The rate of transport through the gas phase was given by a retardation coefficient, which was in terms of the amount of absorption onto the solid phase through the water and the amount of absorption into the water from the gas phase, which gave the rate at which, the delay rate, if you like, of the velocity by diffusion or advection in the system. So in other words, if you know the advective velocity of vapor flow, you know the gaseous retardation coefficient, then the effective velocity at which those contaminants will travel is just the advective velocity divided through by the gaseous retardation coefficient. If it was washed down by water, you could calculate the rate at which it was washed down by the infiltration rate divided by the effective moisture content. So we're assuming that the moisture content in the soil doesn't change, And so all the water that comes in at the top end moves down through the system in the existing saturation or moisture content. And therefore this is some kind of basically an advective flux of how fast the front of this saturation pulse carrying the stuff from the surface is moving down into the subsurface. So this is the advective velocity. If you know the advective, so this is the Darcy velocity, the advective velocity, which is moving from. If you want to calculate the rate at which it's moving, the mass loading of the system, then you take the advective velocity, the advective velocity times the volumetric moisture content gives you the Darcy velocity of the water. Darcy velocity times the concentration gives you the mass loading rate per square meter, basically. So we talked about that, and I guess that was basically as far as we got. We talked about remediation, but we didn't talk about that, so that won't be on the test. And we talked about site characterization, but that's maybe the stuff on direct methods could turn up on the test, but not on indirect because we didn't cover that. Okay, so that's basically it. Great. All right.
Enter your PIN, followed by pound.